Here's part two. When I took organic chemistry in undergrad, I remember learning in Gen Chem, I learned a lot in Gen Chem, but I did not remember formal charge much. And then on like the, I don't know, second week of organic chem, the professor said, here's how you calculate formal charge really, really easily without worrying about the equation. And formal charge is calculated by this, the fast way, when you can see the structure. It's the number of valence electrons that it has normally, just naturally, that atom, minus the number of lines, minus the number of dots. So let's calculate formal charge for this carbon here. Carbon has 4 valence electrons because it's in the fourth tall group. So it's 4 valence minus away. How many lines are touching it? 4. And then how many dots? None. There are no lone pair around that carbon. So the formal charge on this carbon here is 0. Valence minus lines minus dots. Let's calculate the formal charge for the nitrogen to the left of it. So this one right here. Now, nitrogen has 5 valence electrons because it's in the fifth tall column, right? How many lines are touching it? 1, 2. So minus 2. And then dots. 1, 2, 3, 4. So that gives us -1. That means that this nitrogen here has a -1 formal charge, and the same thing can apply. You can use that same basic equation for this oxygen here. This oxygen, all oxygens are going to have 6 valence electrons because it's in the 6th tall column. Subtract away how many lines are touching it, 2, and how many dots, 1, 2, 3, 4. 6 minus 2 minus 4, there is a 0 formal charge on that oxygen. Now, formal charge is cool because it can help you identify what the best structure is, which we're doing here. Which of the following resonance structures for the isocyanate ion is the major resonance contributor? Which means the one that has the most minimized formal charge. Now, the overall charge on the isocyanate ion is -1. And if you think about it, kind of makes sense. Add up your formal charges. -1 plus 0 plus 0 is -1. That means that the overall thing better have a -1 charge, and it does. So the sum of all the formal charges for all the atoms in a compound must add up to the overall charge. Now that means that for all of these structures, you're going to have a -1 somewhere. When it comes to picking the best resonance structure, the resonance structure that's going to contribute the most is going to be the one that gives the formal charge to the one that can handle it best. So let's go through and calculate all the formal charges real quick. Get rid of those, that. Okay. Let's go to the first one. This central carbon, because carbon has 4 valence electrons, so 4 minus how many lines touching it? 1, 2, 3, 4. No dots. Carbon likes to have 4 bonds, or 4 lines, I should say, touching it if you want to think of it in a fast way. No formal charge. What about the oxygen over to the right side? Oxygen has 6 minus 1 minus 1, 2, 3, 4, 5, 6. This has a formal charge of -1. And then let's calculate more slowly the formal charge of the nitrogen here. Nitrogen has 5 valence electrons. Subtract away the 3 lines touching it and the 2 dots touching it, and it has a 0 formal charge. Good, makes sense. Our formal charge is there. Let's do C. Nitrogen has 5 valence electrons minus the 1 line minus the 6 dots. That's a -1 formal charge on this nitrogen. Let me double check that. 5 minus 1 is, hold on, my brain, -2. Okay, that did not make sense. There you go. So 5 minus 1 minus 6 is 5 minus 7. That's a -2 formal charge on that nitrogen. That's not looking great. And then that carbon still has 0. If you don't believe me, you can try it out. 4 minus nothing. And then this oxygen over here, it's going to be, oxygen has 6 valence electrons minus the 3 lines touching it minus the 2 dots touching it. 6 minus 3 minus 2 is +1. Now double check your work and see, do the sum of these formal charges add up to the overall charge? Sure they do. -2 plus 0 plus a +1 equals a -1. So all these formal charges are correct. Now you're like, well, which one is the better structure? Here's how you can decide that. The structure where obviously you can't get all 0 formal charges everywhere for every atom. That's just not going to happen. But which one is the best option? The answer to that is the one that the negative formal charge is going to go to the more electronegative atom. So if you look at the periodic table, let's actually find this again. We see here that oxygen is more electronegative than nitrogen, which is more electronegative than carbon. So these three elements are connected on the periodic table, but you notice how the electronegativity increases as you go toward fluorine. Because oxygen is more electronegative, if any atom is going to have to take a negative charge, it would be oxygen. So here's the takeaway. When you have to assign a negative, I should say, when you have to assign a formal charge, a negative formal charge, it goes best on the more electronegative atom. So the reason that this is the best structure is because it gives nitrogen a 0, it gives carbon a 0. Now you can't have oxygen be 0, but if anyone's going to take, pick up the slack, so to speak, the oxygen will take the -1 charge because oxygen is electronegative anyway. So if it's going to accept those electrons with open arms, so to speak. This is not the best one because nitrogen is electronegative, but oxygen is more electronegative. So it would actually prefer to give that negative charge over to the oxygen. And this is a really bad structure because you're giving oxygen, which is very electronegative, a positive formal charge. So this would actually be the least likely resonance structure. So that's why it's A. Number 17, which of the following molecules is or are polar? Definitely got to get into the habit of learning how to draw them out. So if we draw CF4, carbon has 4, actually I'll do it the slow traditional way. So you have carbon, you have your 4 fluorines around it. We haven't bonded them yet. So if we were to draw the Lewis structure for carbon tetrafluoride, it would actually just look like this. And then all those valence electrons all around the fluorine. In 3 dimensions, it would look something like this. Sort of. I'm not going to draw the lone pair on these as well. But this is a tetrahedral shape. Now, here's a really big clue / takeaway. Whenever you have a tetrahedral shape and every edge element, so every outside atom is the same, it's not polar. So this is not polar because, sure, the carbon-fluorine bond is absolutely polar. Fluorine is going to pull electron density toward it in every carbon-fluorine bond. But it's overall not going to have a dipole, or it's not going to be polar because all the fluorines cancel out part of another fluorine. If you were to flip the carbon tetrafluoride molecule as many times as you want, it's just going to look the same all directions. This is nonpolar. So again, whenever you have something that has 4 atoms connected to the central atom, and every single one of those outside atoms is the same, and there's no lone pair on that central atom, it's not going to be polar. So there's a couple of things to think about. I guess I'll put the first clue. Same outside atoms. Scroll down a little bit. If it has all the same outside atoms, and this is a general rule, if they all have the same outside atoms and there's no lone pair on the central atom, then it's going to be nonpolar. That's like the fast and dirty way to kind of think of it. And this definitely applies here. It's all the same atoms on the outside, no lone pair on the inside. This is going to be nonpolar. Now, it has polar bonds, but there's a balance. Now, let's think about SO2. Sometimes you really do got to draw them out. I'm going to shrink those down. All right. SO2, sulfur dioxide. So sulfur has 6 valence as the oxygens, so there's going to be 18 valence electrons to use. So we have S and 2 O's. We don't really know how they're oriented yet. Let's just pop them down. Now, of my 18 valence electrons, you got to use at least 4 to connect them, right? So minus 4, that gives me 14 remaining. Those remaining 14 electrons are going to go on the outside first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I still got to put 2 more down, 13, 14. That's not the final structure because that sulfur is electron deficient, and it's not beryllium or boron, so it can't be electron deficient, which means it has to satisfy the octet. Now we can't add any more dots or lines without taking one away, because remember, all the electrons that are available for bonding or lone pair are currently on the screen in front of your face. However, what will happen is that one of these oxygens, it does not matter which, will form a double bond with the sulfur, and that's your structure. Let's count our electron groups though. Around that central sulfur, we have 1, 2, 3 electron regions. Now, if you want to kind of classify those electron regions, there is one lone pair on that sulfur, and there are 2 bonding areas. Bonding area over here, there's a bonding area over here, and there's your lone pair. That means that because this is trigonoplanar, or whoops, I accidentally said that too fast. Because this is 3 electron regions, it's going to be a trigonoplanar electron geometry. That's the electron geometry. But what's the actual molecular shape? Well, let's draw this out a little bit better then. Sulfur is going to have that little lone pair up there, and then you have a double bonded oxygen and a single bonded oxygen. And this overall leftover shape, that's what we call bent, right? Bent follows this code here. Sure, electron region is trigonoplanar, but the molecular shape is bent because one of those regions is a lone pair. Now, if you don't believe me here, you can go back over to this thing and make your own sulfur dioxide, which I'm sure is on here. There it is. Perfect. Now, of course, this actually has double bonds on both sides. That part does not actually matter because we know that sulfur can be hypervalent. So if you want to minimize the formal charge, have a field day with it. But this is still the correct shape. The electron geometry is trigonoplanar. The molecular geometry is bent. Here's what you've got to understand is if I were to have the simulation where I'm looking at the polarity, which I don't think... This one, there is another simulation that's kind of like this where you can see the dipole arrows. You can kind of see here that this is not a balanced molecule. So back to here, if we were to draw the dipoles, let's see, oxygen is more electronegative. Well, here's the takeaway from that really fast. Bent, polar. So that's a really easy one. In general, I can't think of any exceptions. If it's bent, it's polar. So this is definitely going to be polar. Now let's draw, shrink that down, go away. Okay, that did not shrink. Let's try that again. All right, so let's draw HCN, which is right here. H has 1 valence, carbon has 4 valence, nitrogen has 5 valence. That gives us 10 to work with. So let's put them in the order that we see them. H, C in the middle, N. Now, again, we have 10 valence electrons to use. Let's bond them all once, and that gives us a lot. We've used up 4 of them. That gives us 6 remaining. Where are those 6 going to go? You may be tempted to spread them out around hydrogen, but never do that. Hydrogen can only hold 2 electrons, which is right here in the bond. So once hydrogen has a single bond, it's done. That remaining 6 electrons are going to have to go around nitrogen. That carbon in the middle is electron deficient. So nitrogen will share in once, and then it's still electron deficient. So nitrogen will share again, and that is why you end up with a triple bond right there. That is the only reasonable structure. So this right here is linear. How many electron regions are around that central atom? 1, 2. So there are 2 electron regions. 2 electron regions is super simple. It's linear, straight up. So it has electron region geometry and a molecular geometry of just linear. Now you might think, are linear things polar or non-polar? That one is not as easy to understand because it depends on what the actual atoms are. But I can tell you now that this side of the molecule, the nitrogen side, has a higher electronegativity and also just a higher electron density than the hydrogen side. This is a polar molecule because in the tug of war of electrons around that carbon, nitrogen is winning, and there is a greater electron density around the nitrogen side than the hydrogen side, polar. And let's try NF3. I'm going to shrink this down. Wait, what is going on there? Okay. It goes away. All right, and then lastly, we're going to draw NF3. Nitrogen has 5, and the 3 fluorines is going to be 21, 5, 26. So we have 26 valence electrons to use when we are plopping our NF3 down. I'm going to move that over here. All right. Now, none of them are bonded yet, so let's bond them once. Our Lewis structure so far has just used up 6. We have 20 remaining valence electrons. Spread them all out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I still have 2 left, so when I run out of spaces to put them on the outside, you put them on the inside. And then that gives us 0, which is always the goal. Great. So the electron counting is done. We have NF3. How many electron regions are around this nitrogen? We have 1, 2, 3, 4. There are 4 electron regions. Let's classify them. We have a lone pair right there. So there's 1 lone pair. And then we have 1, 2, 3 bonding areas. So if you look at your Vesper theory chart, when there are 4 electron regions, that means that the electron region geometry is tetrahedral. Now, don't fall into the trap of thinking, oh, well, he said in the video that if it's tetrahedral and all the outside atoms are the same, then it has to be nonpolar. Because remember, if there are no lone pair, that's the case. But this has lone pair on it. In general, when something has less than 5 electron regions and there's lone pair on that central atom, it's typically going to be polar. That's your clue. So underneath here, we see that because one of those electron regions is a lone pair, the resulting shape is trigonal, not flat, it's trigonal pyramidal. Here's what it looks like. If we go back here, I'm sure NF3 is on here somewhere. Nope, but same thing. Actually, let's go to models. All right, so let's build it from scratch. So here's our nitrogen. Just pretend like that's nitrogen. We're going to add a fluorine, a fluorine, a fluorine. Right now, it looks like it's trigonal planar. But don't forget, there's a lone pair. And now we call this trigonal pyramidal. Notice how the atoms on the bottom are not equal and oppositely canceling out another atom. There's that lone pair on the top that pushes those atoms and those bonds down. And in general, whenever there's a lone pair on the central atom, it's going to be polar. If we're talking about, something that's not hypervalent. So it's going to be P for polar. So it asks which of them are polar. 3 of them. This one, and this one. Not the first one. My tip for you is, gosh, there's a lot going on here, but basically know how to draw Lewis structures, know how Lewis structures, which are 2D, easily translate into Vesper theory, which is 3D. Recognize that you have to consider both geometry and electronegativity when you're determining if something is polar. 18. How many of the following species have a central atom with an expanded octet? Note that halogens usually attach to the central atom via single bonds. So again, you had to draw these out. Xenon tetrafluoride. And after seeing these for a while, you kind of start to memorize the shapes and what they tend to look like. But xenon tetrafluoride actually has it on here. Xenon is one of those things that can do an expanded octet. So here it is. This shape right here is square planar. That's the molecular geometry. Notice how those 2 lone pair technically they go equatorial if you want to look at it kind of like this. All right, so we have an expanded octet here because that central atom has 2, 4, 6, 8, 10, 12 electrons around it. Now, how do we prove that? First of all, you got to recognize on the periodic table that when you have your periodic table, expanded octets can only occur in the second row or below. I think the general idea is like P, phosphorus, and below are pretty okay doing expanded octets, or like silicon and below, but basically you're not going to have nitrogen and oxygen and fluorine giving you expanded octets as central atoms. So let's see, move this, delete. All right, let's draw xenon tetrafluoride. Xenon has 8 valence. There's 4 fluorines, 4 times 7 is 28, plus 8 is 36. Yeah. All right, so let's draw our xenon in the middle. Here's how you know it's going to have an expanded octet, because you have no other options. So xenon in the middle, fluorines around the edge. Let's bond them once. So if I bond them once, 1, 2, 3, 4, 5, 6, 7, 8, I just used up 8. That leaves me with 28 remaining. I'm checking my math here mentally because I feel like I could screw this up very easily. All right, so I have 28 remaining. I'm going to put those 28 around the edge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I've just used up 24. That leaves me with 4 remaining. Oops. 4 valence electrons left. And, like, where do you put them? You've used up all the bonds that exist. You used up all the space around fluorine. The only other place is to put those lone pair around the xenon. And that's an expanded octet. Because if you count how many atoms or how many electrons are touching xenon, 2, 4, 6, 8, 10, 12. Just like we saw with that three-dimensional model over here with the real molecule. This is what it looks like. As a model, of course. All right, that's definitely one of them. Expanded octet. Now, tellurium fluoride, you kind of just draw these out, and that's how you solve problems like this. I can tell you that. Let's actually draw NO2 so you can see how that's not the case there. Because it's the odd one out. As I said, you can't have expanded octets with something that's in the first or second period. Or sorry, first or second, period. So again, I'll add this. Nitrogen is just not deep enough in the periodic table to even allow it to be expanded octet. Nitrogen, all of these things, they just can't be expanded octets. They're just not big enough. So that's one clue. I mean, bromine is low enough. Tellurium is, did I say that right? Yeah, it's low enough for sure. Antimony is low enough, and xenon is low enough. So that's just a huge clue about expanded octets. But if you were to draw, if you were to draw nitrogen, or the nitrite molecule, the nitrite ion, you would do it like this. 5 valence for nitrogen. Each of the oxygens has 6 valence. And if you do the math with that, you'll get an odd number. But don't forget, there's a negative charge, so don't forget to add that extra electron in. And that'll give you 3 times 6, which is 18 valent electrons. Nitrogen in the middle, oxygens wherever they go. You can fix the shape later. First step is to draw, or to bond them once. So 1, 2, 3, 4. I just used up 4. That leaves me with 14 left, which are going to go on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just used up 12. That leaves me with another 2 remaining, which got to go on the inside. Very common for people to stop right there and be like, I'm done. You're not done, because that nitrogen is electron deficient. It's not beryllium. It's not boron. It has to have its octet. And right now it only has 6 electrons. So what do? Just form a bond. Just pick one. Let's pick this one. And now we have a double bond. Now, if you kind of like think about the electron regions around it, you have 1, 2, 3 electron regions. So you have 3 ER. That means it's going to be a trigonal planar electron region geometry. But if you kind of think about it, just 1 lone pair and 2 bonding areas, that's going to give you a final shape of bent. In case you cared about that, because I think Vesper's kind of neat. Now, that's the one that can't do an expanded octet, so that's why you're going to have 1, 2, 3, 4. That's your answer. If you were to have a question like this that's similar, and maybe you had NO2 minus, and then you had something else, just recognize what I said earlier. You basically have to be beyond silicon in order to allow yourself to have an expanded octet. Right. Number 19, the best structure for COCl2, where C is essential atom, should show this. I like questions like this because you have to draw it out to get it correct. And this is going to come right back down to Vesper theory. So you have to draw it. Please don't try to BS it. COCl2. Count up your valence. Carbon has 4 valence. Oxygen has 6 valence. There are 2 chlorines. Each of them have 7 valence. That's 10 plus 14. That is 24 valence. So I have 24 valence electrons in my bank. And I'm going to put carbon in the middle. Oxygen is going to go around there somewhere, as are the 2 chlorines. Of my 24, I've used none. So let's use up some of them. Bond them once. 1, 2, 3, 4, 5, 6. You gotta bond them at least once. That uses up 6 of your valence, giving me a remaining 18 valence to use. Spread those 18 remainers around the edges first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You feel done. Very simple, but you're not done. It is true that you've used up your 18 valence electrons and you got to 0, which is what you want, but you gotta always check to see if they have their octets. This carbon in the middle does not have an octet. So if you were to answer the question incorrectly based on an incorrect Lewis structure, this will have 3 single bonds, no double bonds, and no unshared electron pairs on the central atom. That's not what we're looking, or even on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so this would actually have 9 lone pairs in the structure overall. This is not the right structure. That central carbon does need an octet, so take away a double and then add a double like this. And there you go. Now, theoretically, you could have put that double bond anywhere. It would have just been a resonance structure. So let's say you're like, well, what if I didn't do that? What if I chose one of the chlorines to make a double bond? Your answer would actually be the same. But let's do it proper, because think about formal charge always. And it would actually be oxygen willing to give up its lone pair. And that would give everybody a 0 formal charge. Here's what that structure looks like if you're going to be correct about it. Now we can analyze it and be like, oh, there's a single double bond. So there's 1 double bond. And then we've got 2 single bonds. And then how many not unpaired, but how many lone pair, you can also call them lone pair. Unshared electrons are also called lone pair. How many unshared electron pairs are there? There's 1, 2, 3, 4, 5, 6, 7, 8. And that's how you do a problem like that. You have to draw it and then analyze it, and your drawing must be right. Number 20, which species has the smallest bond angle? Again, drawing is going to help you, as well as understanding Vesper theory. So let's kind of let's do a little sketch for these. Let's see. Chlorine is 7 plus oxygen is 2 times 6. Now this is a plus charge, so we're going to subtract away an oxygen, because remember, plus means you lose an oxygen. So 7 plus 2 times 6, 2 times 6 is 12, plus 7 minus 1 is 18. We have 18 valence electrons. Let's just do that for all of them. This one's going to add 1, so it's going to be 20. And then this one's going to add another 6, so it's going to be 26. And this one's going to add another 6, because we're adding another oxygen. Every time you add an oxygen, you're adding 6 valence electrons. So that's why it's going to 2, going to 3, going to 4. I'm just adding 6 every time. That's going to be 32 valence. And if you sketch them out real quick, so chlorine in the middle, oxygen's on the outside for this first one. Oh, by the way, because... Well, learning to sketch them out is helpful, but you'll probably find a pattern here. So if you're like, oh, I understand this question, then you can skip to the end or go to another one. So this one is, we have 18 valence, bond them once. We now have 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We are going to fix it up like this. Now, if you were to sketch this out more properly, this would have this overall shape. So I guess I'll kind of do them in shapes like this. It would have a double bond, and then a single bond, and then your lone pair. And what we have here is a shape that's like less than 120. Because remember, lone pairs take up space. It might be like 117 or something like that. Let's take a look at... Yeah, this is a tricky one, only because I could see a lot of people picking the fourth answer if they don't draw them out. So let's draw out another one. I guess I'll label them. First one, second answer. Let's do the third answer choice, so you can see why they're not right. ClO3. So we have 26 valence electrons to use. We have Cl, we have 3 O's we can pop around. Of our 26, we're going to use up 6 immediately to bond them, leaving us with 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now we have this shape, which is trigonal pyramidal. So we have our lone pair up there. We have an oxygen over there. We have an oxygen kind of coming out like this. We have one in the back like this. This shape right here, or that angle I should say, is kind of like 109.5, but even a little less than that. So a little less than 109.5. So we're going to say less than 109.5 because it's tetrahedral electron geometry, but it's like one less because remember, or a little less because a lone pair take up space. For this first one, I'm just going to write it out so we have it. Get rid of this extra stuff. Put an E answer there. All right, we said that was less than 120. When we say less than, we mean it's close. We don't mean like, obviously the number 4 is less than 120, but we mean it's close. We don't want to be not mutually exclusive. All right, and then ClO4, if we were to draw that one out, it would be Cl, I'm going to shrink these because they're like too big right now. Whoops. Shrinking is weird on here. All right, let's see, ClO4. So let's put those 4 oxygens around the edge. We have 32 electrons to use. To bond them all once to that chlorine, it's going to use up 8. So minus 8 gives us 24. Those remaining 24 are going to go all around the edge. And then that actually finishes it off. So this would be a tetrahedral shape, which looks like this. So let's duplicate this. But instead of a lone pair, it's actually just a real actual bond up there again. Now that gives us a shape of just 109.5. So we have just 109.5 here. So those are those angles. What is going on with ClO2, which is the chlorite ion? Let's shrink that down. Actually, mark it first and then shrink it. Whoa, not the whole page though. Chill out. All right, move that over here. So what's going on with the second one? We have 20 valence electrons to use. So let's put Cl in the middle and our O's around the edge. That's too far. There's better. All right, so of our 20, we're going to use up 1, 2, 3, 4 to do the basic bonding. That gives us 16 remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ooh, interesting. Because now notice how our lone pair, or how our central atom has 2 lone pair. And as you heard earlier, every time you add lone pair to that central atom, it makes the angle even smaller. So if think about like this one has no lone pair, 109.5. This central atom has 1 lone pair, less than 109.5. So luckily this feature is great. I can duplicate. To draw this one out, I would actually add another lone pair here off in the back, and this is even less than that. If you want to be technical, I really don't like the less than and then like less than. I prefer real numbers, but it does vary. Basically, if this was less than 109.5, this is less than even that. It's really like 104.5, by the way. If you're like, what is the real number? It is approximately, very roughly, every time you add a lone pair, subtract 2.5 degrees. If it really helps you to quantify it, that's why this angle right here is really like 107-ish. If it really helps, like, okay, he said in the video, every time you add a lone pair to that central atom, it's like minus 2 to 3 degrees, roughly. That might give you a marker for understanding why this is the correct answer. Because it has the most lone pair on the central atom. But this is a cool question. Well, I think it is, because you don't know that unless you draw them out. It's very, very tempting to put this one, because you might think, oh, central atom with 4 outside atoms, this has got to be tetrahedral. But it's actually this one, because this has a tetrahedral electron region geometry as well. But because 2 of those electron regions are actually lone pair, it's going to squeeze the angle down even more. Number 21. Vesper 3 is exhausting. I'm just going to say that. I hope this does not take y'all super long if y'all are taking this on a Friday night. But drawing and analyzing structures can be a little bit much. So now you're like, okay, which of these are flat or planar? All right. The first one, we can kind of draw out the first one into F plus. Remember, when there's a plus sign, you subtract an electron from the overall count. When there's a minus sign, you add one. Excuse me. So let's draw the first one out. Let's see if I can do some color coding this time. I'll do the first one in purple. So how do we count up those valence? Well, it's going to be 5 for the nitrogen. Actually, there's 2 of them, so it's going to be 2 times 5. So that's 2 times 5 is 10. Plus, we're going to add in the fluorine, which is 7. But we're going to subtract away that electron because of this. So 10 plus 6 is 16. So there are 16 valence electrons for that first thing. So put nitrogen in the middle. Fluorine's on the, whoops, there's 2 nitrogens. So put one of the nitrogens in the middle, one to the left and one the fluorine to the right, or however you want to do it. You could have done F and N too, that's fine. And then let's connect them once. 1, 2, 3, 4. I've just used up 4 of my 16. That leaves me 12 remaining. Now we have 12 there. I've used up those 12. I've got 0. That's good. But remember, nitrogen cannot be electron deficient. As a clue, just from having seen lots of these structures, nitrogen is in a good place when it has 3 lines touching it. But remember, count formal charge, you can kind of see how that pattern works. So let's help out this central nitrogen, which is electron deficient. It's sad right now. So to fix that, let's pick one of these and make a double bond. It's still unhappy because now this nitrogen has 6 electrons touching it. 2 per line, right? So let's pick the other nitrogen to sacrifice again. And there we go. I'm going to move those electrons over here just because it looks better. All right, now what about that charge? As a reminder of formal charge, just count them up. Formal charge is valence minus lines minus dots. How easy. Let's do the first nitrogen. Nitrogen has 5 valence because it's nitrogen. Minus how many lines? 3. Minus how many dots? 2. This first nitrogen has a formal charge of nothing. That's a happy nitrogen. I don't like to give personalities to atoms, but sometimes it's fun, so I'm going to do it anyways, even though we know they don't think. And then nitrogen in the middle has 5 valence because it's nitrogen, minus 4 lines, minus no dots. So that's a plus 1 formal charge. And then we're looking at the fluorine on the edge. Fluorine has 7 valence, minus its 1 line, minus its 6 dots. That's going to be a 0 formal charge. All right, we have our formal charges. If you add up the formal charges, 0 plus 1 plus 0 is plus 1. Verify that everything's good. This is what it looks like. Is this flat? Tricky, because it's linear. So, technically a line is flat. I don't know. That's a little bit semantics. We'll come back to it. But basically, I would say it's not flat. It's a line. So we'll put that over here. And that's what it looks like. We can get rid of those. All right, now they're going to be faster. SO2, we already saw from earlier. It's going to look like this bent shape. And whether you have a single double bond or double bond, it does not matter. But this is what SO2 looks like, if you kind of want to give it a little bit of Vesperness. It has a shape of trigonal planar, an electron geometry of trigonal planar. So the electron geometry, the EG, that is trigonal planar. So it does have the word planar in it. So far, we are certain that this one's flat. I would also argue that the first one is flat too, based on semantics, but I'm not sure. I don't know. I think lines are flat. So it's just like a little geometry trickery there. It's not 3D, but they're all 3D, but you know what I mean. Anyways, that's the first one. Let's kind of shrink that down and move it. We already know what SO2 looks like, so there's no point in me going through the drawing for it. We also drew already HCN, which we know looks like this. It's another linear molecule. That would be considered flat, I would say. So let's move that down. Once you start drawing structures, professors can't use but so many simple structures for covalent things. So you'll start to see patterns. Okay, CF4. We already saw that one too. That one is carbon tetrafluoride, which looks 3D-ly like this, kind of. You get that tetrahedral shape. This is very much not flat. This is tetrahedral. Tetrahedral isn't flat. It's like a little pyramid with a. It's like a little pyramid with a triangular base. It's a tetrahedron. It looks like this. That's not flat. So nope. We would say that that is not flat. So we would not include that. And then you have H3O, which is the hydronium ion. Let's do that in orange. Let's see. Let's actually draw this one out from scratch. So hydrogen is 1 each. So it's 3 times 1 plus the 6 from the oxygen minus the 1 because it lost 1. And then that's 8. So there's 8 valence. Oxygen's in the middle. The 3 hydrogens are on the edge. Of my 8 valence, that looks terrible. Of my 8 valence, I'm going to connect them all once. And then the remaining 2 are just going to go on the oxygen. This is your hydronium ion. If you count the formal charge of the hydrogen, it's going to be 0, obviously. But the formal charge on the oxygen is going to be a +1. 6 minus 3 lines minus 2 dots plus 1. All right, just in case you're like, what's the connection between shape and formal charge and all this other stuff that he's been talking about. So get rid of that. Don't care about the formal charge for real. And it's not flat. Why is this not flat? If you count your electron regions, you have 4 electron regions, right? And as I've said a million times, 4 electron regions means it's going to have a tetrahedral electron geometry. But when you break it down into like what is it really made of, it's 0, whoops, not 0, I can count. It's 1 lone pair and 3 bonding areas, right? This is a bonding area, this is a bonding area, this is a bonding area, and then obviously we have our lone pair on that central atom. So the shape here is going to be trigonal, but it's not trigonal planar. That would literally mean flat. It's trigonal pyramidal or trigonal pyramidal, however you want to say it. Let's model the hydronium ion. So go to a model, 0, build, clear. All right, that's our oxygen in the middle. Now, the oxygen has 1, 2, 3 bonds, right? Those are like the 3 hydrogens. But remember, we just said it's not planar because there's a lone pair on it. And now you can see this is very much not flat. It's got a little bend to it, which means it is polar, but also it ain't flat. So going back to here, disqualified. So yes, flat would also include lines. And that would be this one, and this one. That's 3 of them. That's why that's the answer. Now, because drawing is exhausting, sometimes I think those questions might take you a little longer, even though there's no math. But you'll learn the shortcuts, or however works for you. 22. Which of the following statements about BF3 are true? Now, boron is one of the special exceptions. Boron can be hypovalent, or it can be one of those atoms where only 6 valence electrons is okay. Because of the way, if you calculate the formal charge, let's do that. So BF3 is 3 plus 3 times 7. So there are how many valence? 24. So we draw boron in the middle, and our fluorines are on the edge. And then bond them once. We've used 6 of our 24. That gives us 18 that's got to go around the edges. And then you're done. Calculate the formal charge of everybody. Everybody's happy. Now, this is flat. This would actually look just like this. BF3 is, there it is. Because it's such a common example, this is what BF3 looks like. You can very clearly see it's flat. Bond angle's 120 degrees. There it is. Trigonal planar. Now, this is not the dipole simulation, but because every edge is the same atom, if you were to draw electronegativity arrows or dipole arrows toward the fluorine for each one, they are going to cancel out. The bonds are polar. If you pull up the Pauling electronegativity thing, you can see that boron is a 2.8, fluorine is a 4.0. The difference in electronegativity is equal to 1.2. So it falls within the polar covalent range. However, because every atom on the outside is the same and the central atom has no lone pair, it's very safe to assume that this is a nonpolar molecule. Even though the bonds are polar, those polar bonds cancel themselves out with the other things, right? That's just one of those exceptions you should know. Always sketch it out, because while BF3, so let's say you have BF3, right? We just drew it. We can see that it's nonpolar because there's no lone pair on the central atom. But if you compare BF3 to, say, PF3, if you were to draw PF3, it would look like this. It would be P with a lone pair, and then you have your 3 fluorines, and this is very clearly polar because you have a lone pair on that central atom. So always look for the lone pair on the central atom if it's polar or not. That's a clue, but don't say it's 100% true. Say it's like 90% true, 95, 99, something good enough to get you through. Let's delete this. All right, number 23. Predict the actual bond angles in N2F2 using Vesper theory. Well, we drew it already, didn't we? Where the heck did it go? Okay, I guess I'll draw it again. It's not too big of a deal. I feel like I drew it somewhere. Okay, wait, I did. There it is. So we're going to duplicate this and move it down. Where did it go? Okay, so we have N2F plus. And we did the drawing already, so if you don't, kind of rewind the video. But basically, you have a line, right? We have how many bonding areas around that central atom? 1, 2. It doesn't matter that it's a triple bond. This is a bonding area, and this is a bonding area, which means that both of those are technically electron regions. And they're the only 2 around that central atom. So there are 2 electron regions around that central atom. None of them are lone pair. There's no lone pair on that end in the middle. But there are 2 bonding areas. And first of all, if there are 2 electron regions, it's linear electron geometry. And if there are no lone pair and all those electron regions are real bonding areas, it's going to remain linear for the molecular geometry. Now, what does that look like over here? Model, clear, 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 clear. All right, here's our nitrogen in the middle. Let's add the fluorine, and let's add the other nitrogen. And oh, look, how magical. It literally is 180 degrees because it's a line. And that's from basic geometry. So 180 degrees. That's why it is what it is. 180. Now, how would you know that? Draw it out and learn how to do the Vesper. Vesper is not too bad if you don't have to go into like the crazier hypervalent stuff too often. For number 24, we already saw that SO2 is such a common one. Like if we were to draw it out again, it's not going to change its overall shape. It's going to still look like this. It's going to have a single and a double, or you can do 2 doubles if you'd like to minimize that formal charge. But here's one possible structure. It's going to be bent. I mean, if you draw it out, count your electron regions, electron geometry, all that stuff, molecular geometry at the end, the molecular shape is bent. Do pay attention to the fact that molecular shape and electron geometry are different. The molecular shape is what's left over. It's what's left over when you ignore the lone pair on the central atom. And what you get left over is the bent shape. So again, SO2, oh, by the way, SO2 could also look like this. This is also acceptable because it gives everything a 0 formal charge. But it still gives you a lone pair on the central atom. So as we saw with this, if we go to real molecules and go to SO2, it's a common example of something that is clearly bent. All right. So let's end this video on 25, and then we'll finish up with the others. The formal charge on Xe, we've seen formal charge. It's really simple when you look at a diagram. Yes, you may think, I have to memorize the equation. I don't have the equation memorized. I could derive the formal charge equation from the whole valence minus lines minus dots thing, but trust me, this is so much easier. So let's do it. Valence for xenon is 8. Minus the line is touching xenon. 1, 2, 3, 4, 5, 6. Minus the dots. 1, 2. There's a formal charge on that xenon of 0. Perfect. Now, if you were asked to determine the formal charge on anything, just make sure you know how many valence electrons it has.